Hello everybody. Welcome back to our computer vision meetup, our monthly. It's nice to see a few people here. I think most of the people thought about they have better things to do in that warm weather, maybe lying in the sun. I'm glad to see that some of you made it here to our computer vision meetup at such a nice hot day. And this is our summer edition, so we won't have a meetup until the end of August. So we will have a summer break, so no meetup in the end of July, which we would have normally. So, sorry. I'm your organizer, Daniel. I'm CTO and co-founder of Anyline. This is our office place. So, I hope you like it. Also, Sabrina is my co-organizer. She does most of the work. I'm just here, face of the meetup. I'm presenting the stuff. And you all maybe already recognized that drinks are sponsored by Anyline. So feel free to grab another beer or focaccia or whatever, or a gin tonic with this mixture. I don't know. And we are looking for speaker. We don't get a lot of speaker, and that's why we have free tickets for the next 10 speakers who want to speak at the next meetup. So, where are the speakers? No? Didn't work? Yeah, for you guys, we also have a free ticket because you're speaking today. So it's for the self-driving tracks. I hacked these slides together in the last 5 minutes because we have a release week and it was really stressful this week. It's for the autonomous vehicle technology demonstration and workshops. It's at the 28th of July at the ÖMDC Desdorf, Austria. There's a one-day training workshop and demonstrations from driverless technology. So, and we got 10 free tickets for this event. So, when someone wants to speak at the next meetup, he gets a free ticket. And for everybody else, we have a 50% discount code. It's this code. Don't forget it. And you can get your tickets at selfdrivingtrackdays.com. I think that's very interesting. So please go for it. And take the option with the meetup dog and the free ticket. So, one more thing what we have to announce, there's an AI summit in Vienna on the 4th of September. And I think that's also great. It's only €8 the ticket, so it's really cheap. It's basically free. And I think the speaker lineup is also very great. Sepp Hochreiter, inventor of the LSTMs basically. Dave Elliott, yeah. Calvin Stewart, yeah, I think the Zalando guy is also not so bad. Yeah, please sign up. I think Anyline will also be there. We will get a startup table. I hope so, that we get one. And yeah, I hope to see you all there. I think it's a great opportunity for AI in Vienna. And also, we are hiring. It's also a very short notice slide. We are searching for a senior Android developer. So if anybody knows someone who knows someone who knows someone, come to me or write at Daniel at Anyline.io or job at Anyline.io or what? Hire me at Anyline.io. I just hacked this slide together 5 minutes before the meetup because that's how early stage it is with the hiring process. We just decided it a few minutes ago. So the first one you get the opportunity to work at Anyline. Yeah, and today's lineup, we have a great speaker lineup. We have Christoph Götz here. He's doing augmenting and protecting the human eye with computer vision. It's very interesting. And afterwards, I will give a short introduction to CoreML, which is a new feature of iOS 11. And I give you a short presentation with a live demo, which I hacked together in the last minutes. Yeah, it's release week. Once again, it was very stressful and is very stressful this week. So let's just get started and continue with the talk from Christoph Götz.
So welcome everybody. I'm Christoph Götz from the team LaserEye, and I'd like to present you our protective smart glass, which is to extend the human vision. And I start with a question. I mean, what you do in computer vision is you make sense of the world. And I mean, have you ever thought of it like, why is there no computer touch meetup, but only a computer vision meetup? I mean, if I touch something in order to see the world, I have to actually interact with the thing itself. It's like my electrons in the hand repulsed by the object. So it actually takes a while. You have to directly interact. Sometimes you don't want to touch something. You're slow and big, and you're only one thing. So if I want to know about there, I actually have to go there in order to know something about it. So it's directly interacting slowly, and you only get low resolution data out of it. But that's not true for vision. You basically have a lot of photons doing the work for you. So they bounce around, they interact with a material, and you detect them. So what you get is basically they interact with all the stuff. They are small and quick, they are basically light speed, and there are plenty of different ones, so even specific interactions. And so that explains why we like get indirectly and quickly specific high resolution data from the universe kind of via our eyes. But the next question, why do we actually see what we see? And that depends on this guy here. It has a special radius and a special chemical composition, and it has a temperature of 5,700 Kelvin. And quantum physics tells us that it emits photons at a certain energy, and the energy translates to a wavelength. So what you see here is that there's a clear peak at around 500 nanometers. And conveniently, our visual range lines up perfectly with this range. So what evolution optimized us for is basically to get the highest information gain per time. Because in this visible range, you just have the most photons bouncing around, so you can get the most interaction with distant objects over time. And so I'm coming from a physics laboratory, and what we use is lasers, and lasers are awesome because of a multitude of things. If you just look at this little graph, like the sun is emitting roughly at the peak 2 watts per square meter of a certain wavelength of photons. But lasers can be used, as they're used in medical or scientific purposes. They emit, for example, 180 watts, but not only per square meters, but per square millimeters. So that means that you get actually a light source which is 90 million times brighter than the sun. And so you get so many photons that you can extract information extraordinarily quickly. So you get lots of information extremely quick, extremely precise, and extremely specific, because you see, well, it's only one single wavelength interacting. And that's why lasers are basically a key technology in science, medicine, and manufacturing nowadays. And they will increase in the future. But well, it's nice to like extract information, but what happens as well is also this. So they also change stuff while they interact, and that can be bad for your eye, because that's a picture of a healthy retina. If you shine a laser, for example, 1 watt for a fraction of a second into your eye, what you hear is like a little pop in your head. That's when your retina is boiling, and then you're blind. So they're really dangerous, and as such, people working with lasers, they face like a multitude of problems. First, they want to be protected. They need to see what they're working with, the laser, and they need digital information at the same time. But the current technology is based on basically like filters. So it's like a special sunglass which blocks, for example here, the green and blue light for 5 to 10 seconds. If you look longer into the laser, then this stuff also burns and the laser gets through and you're blind. Also, if you use a red laser, it goes through because, well, you've got to see something. So they are always transparent, and you're never fully protected. Also, if you have like a blue and a red laser, you're basically fucked. And there's actually no no protection out there available at the market right now for this case. So this is basically what you see before. You have some nice oscilloscope, but if you wear the protection, the stuff you're working with, the laser gets invisible, and also the data vanishes. Then the next problem, you gotta have one goggle for every application you have out there. If you have a red laser, you need a green goggle. If you have a green laser, you have a red goggle. If you tune up the power, you need a different goggle. So there are like 8,000 different goggles out there. You have to read these very intuitive descriptions in order to pick the right ones. And then you gotta find it when you need it. Like you tweak something and you gotta change it, otherwise you're not protected. So I think I could convince you that the current technology is like not so great. It doesn't offer full protection. It makes the stuff you're working with invisible, and well, you don't get more digital data. So while working in the lab, we thought like, what's the actual best protection? And that's it. The world's best eye protection doesn't get you any photons from the outside to your eye. And that's exactly what we want to build. We take the light and we block it. So basically, nothing comes to the eye, but you also don't see anything. So what we want to do is put a camera in front of your eye and then project the outside world back. So you see basically as before, you see colors and even a little more, and I'm gonna explain that now. So that's basically our product, Laser Eye. Looks a little bit better, I guess. Because as I showed you, the visible spectrum is only like a super tiny part of the actual electromagnetic spectrum, but the lasers which we're using daily in the lab are all across the scale. So those ones you could see, but you don't want to see them because then you're blind. So you actually never see them because you wear the protection, and those you can't even see because, well, they're invisible. So how could we solve that problem, or how would biology solve that problem? Like humans have 3 color receptors, but if you look at this little fella, the mantis shrimp, and how he dresses like on a normal workday, he's a little different because he has actually 16 color receptors. So that means, I always ask myself the question, like, are we missing out on something? I mean, if you look at him, maybe. And if you work with invisible lasers, then for sure. And that's another comparison where you basically, all the flowers which you see are not what they really are because they're designed for bees, and they actually see a much nicer picture, or even birds. So what we could do is change the eye. So the eye is built up like this. We have, well, the whole optical apparatus, which the light travels through this whole mess to the actual receptors and gets absorbed by some very tiny nanometer big molecule, which is this one, retinol. So what we can do now is basically take this, and when light hits this one, it like goes from an elongated to a tilted conformation, and that's basically what we do when we see. That's the signal. So what we can do now is basically take that information, copy the genetic code, it's just a sequence of bits, basically, paste it into a bacterium, and then hit compile and purify it, and what you get is a little tiny glass full of like red pigment. That's awesome. But biology doesn't stop there. It can mutate, or we in the lab can also mutate it. And what you do is you basically, since we as like cellular organisms are basically, every cell is kind of like a little 3D printer which aligns atoms in space with nanometer precision. That's why this thing looks like it looks, right? So, and that's coded in the genetic code. So if you change the genetic code, you can add a little charge here. And what it does is it brings like some charged thing to this retinol, this absorbing molecule, and it pulls on it a little bit. And so what happens, it changes the spectrum of absorption. And if you go further, you can actually make the whole funky spectrum. And then the next thing would be to actually take this genetic code, put it back into those cells, make compile in your eyes, and then you could see fancy colors. But that's a little difficult, I think. So what we do instead is we just use a camera which detects basically twice the spectral range of the human eye. And with that, we see like those visible lasers, but also like invisible lasers far above what's capable for the human eye. And also by adding extra senses, we can even extend this range to well, I don't know, stuff that's far beyond. So we solved like how to see invisible things, but also since we have two screens in front of our eyes and a smartphone on the head, we can also display digital data, and that's where like the computer vision fun starts. Because, well, I mean, in the lab or in medicine, you work with a lot of digital data, which can be like augment your workflow in a lot of different ways. So just to show you how that looks in reality, quickly. When you start your work, you have to basically choose the right goggle based on these intuitive inscriptions here. And as you see, you have to buy a lot of those goggles. This one, for example, costs 1,300 euros. Each user needs one, and each laser type needs one. So what you do, you enter there, you put on your protection, and everything gets really dark, and you basically turn colorblind. That's this nice little oscilloscope, and like, guess which of the buttons is the blue one? Yeah, that one. And that's exactly what you do while working with it. So you basically compromise your security in order to work properly, and you constantly like look over it in order to work properly. But not only the data vanishes here, also the normal laser you're working with is just gone. So imagine building a wall and you don't see the bricks. It's this situation. But in addition, this little tiny spot down there, that's actually invisible light. That's like 1,064 nanometers, and we see until 700 nanometers. So that's far beyond what's possible to the human eye, but the camera still picks it up. And well, the fun part is you can use all this digital data in order to implement security features or give you a direct feedback of what's actually happening on the table, because everything you do goes through a computer until you actually can work with it. And we just want to bring it to the people when they need it the most. Yeah, so I think like humanity deserves better vision, at least those poor fellas. Okay. So yeah, so that's kind of the prototype, or well, a mock-up of it. But virtual reality goggles are getting like really tiny and really nice to work with. This guy is like 88 grams heavy and has it's kind of like an Oculus Rift, but super flat. So your cameras are close to your eye, so you don't like stand in front of yourself, which is quite helpful. And that's the team. So Ur works every day with 14 different lasers in the lab. He's a quantum physicist. And Philip is also a senior postdoc who builds electronic hardware since he's 3 years old and really wants to be a cyborg one day. He even takes holidays to sit at home and code and build stuff. And I studied human vision and cognition and image processing. And together we want to create the hardware which will give basically replace the whole analog filter goggles with one digital solution and even be safer than ever before. Also provide infrared vision and run a lot of apps on it, which we then sell to medicine, research, and industry. And an example here, for example, what those lasers do and how they're used. That's laser which is used in dentistry. So this would be your mouth, basically, where they cut your flesh inside your mouth. And well, they're pretty powerful, as you can see here. But here also the problem. What you actually see while you're working with those is just the visible aim laser. So that's like a little nice green dot. However, the truth is that the actual infrared laser is 1 × 2 centimeters big. So you don't really know where you're working. And I think it might be nice to know for the patient and the medical doctor in order to increase its accuracy. And since we can implement fancy sensors, we can also overlay the picture, for example, with temperature information, because it's also nice to know whether you boil your patient or he's fine. So that's one application. Another one would be where dentists, for example, they scan the tooth, so they have a cut model of the tooth, and while working with lasers and this 3D model, we can basically recognize from the image record which one it is, or provide like training inside a virtual reality goggle in order to not train the procedure in your mouth, but actually do what they, or that they, when they get to the patient, they're actually already ready to do their best job. Yeah, and with this, I thank you for your attention, and welcome for feedback and suggestions, and also you can spread the word about it. And so, yeah, thank you very much. Yes.
The obvious question, how far along are you in development?
So we currently build the prototype, which is we get the crucial part is the fast processing, like getting the camera picture very fast to the display. Because you don't want to have like a delay of 100 milliseconds once you turn your head in order to like motion sickness. So for that we need a very fast processing, and that is like FPGA programming, which we currently develop. Also the whole image distortion and HDR processing, etc. So we got the individual parts are basically there. We just like getting them together and properly running. But we already obtained like first customers which want to have it, so that's kind of our goal right now. We're in the development. We're like a hardware-based team, but still in the end we need software developers who do computer vision, because what you get, like you get every pixel you see, you can actually manipulate. You can, I mean, my dream would be to have kind of a open source app platform where everyone can use this goggle and modulate the reality which he sees, and then share it with other people who can download it and then use this visualization in order to do stuff a different way. So yeah, we're still in the early prototyping phase.
What kind of sensors do you use? Sensors?
It's a standard CMOS camera.
One? Only one?
Two.
For all the wavelength?
So from 350 to 1100 nanometers, you can use a simple CMOS camera. For higher wavelength, you need to go to gallium arsenide, which is, they have a shitty resolution, but you can kind of blow it up artificially. Yeah, so these would be kind of, the idea would be to make a modular interface where you can select the sensors which you need in order to work with your application the best way. And if you take those, for example, those sensors which detect 10 micrometers, you get a temperature sensor for free, because it's like this infrared radiation which people use in the, to detect like heat leaks from buildings.
Right now you can basically project back the image,
Mm-hmm.
but you cannot do something, some reasoning on the image.
Exactly, that's the...
And what would be a common task?
A common task would, for example, be to recognize things in the lab, like small numbers, and look them up immediately and then display this data, or build the streamlined process that people can just get the digital data which they produce in the lab into their field of view, or have actually other people look through the eyes of the experimenter and share their view to the rest of the world, and also make annotations in there. Or the whole object recognition field, for example, for science, is very important to reproduce your your setups. So it would be nice to basically have a look at it and then automatically three-dimensionally reconstruct it, for example, a lot of things. It's the good thing is that the hardware is just the start. You can sell it by yourself because it gives you this invisible information, which is there already. You don't need to generate it computationally. But it opens up this whole new dimension of information, which you can use to display basically everything. So it's kind of, we didn't attack it yet fully because we are not software developers from computer vision, but we already identified a plethora of like applications which people are willing to buy for. Because healthcare is getting more digital, labs are getting more digital, and industry, like with predictive maintenance and Industry 4.0, they create more and more content which can be displayed and help.
Do you have a Wi-Fi component or something?
Yeah. Exactly. So that's we have like two FPGA, which is making the real fast pass-through, and then an additional CPU which runs an Android system which feeds in additional information. Not as quick, but that's also not crucial, let's say. Because well, what you need is like true vision, because you replace the eyes. So, but so we just see it like as a huge playground which other people can use in order to develop their own ideas to help researchers, medical professionals, and industry professionals.
Are you planning to make the hardware and the system open access, or?
Yeah, that's the problem, right? It's a security issue and also liability for us. So what we would like to do is have an app store a little bit more exclusive, like Apple's App Store, where we test the application if it interferes with, like, you know, it shouldn't make like any kind of epileptic seizures and stuff while you work with a laser. Yeah, but then admits to bring it to the people like that.
So basically you have the part of the development is really the level of the hardware.
Mm-hmm.
And also the augmented reality part.
Yeah.
So you are currently at the stage of developing the hardware
Mm-hmm.
and to get the camera right, like with the least possible latency and everything. Do you plan to build the augmented reality system for it from ground up, or use something already existing, or what's your plan?
We would be very happy to use something existing. I mean, there are plenty of people out there who can do it better than us, I would say. So why reinvent the wheel? I mean, we focus on the very most simple things, like just fancy 3D augmentation which interacts with the real world. I mean, it looks awesome, like this mixed reality stuff. But if you ask people, what would they need it for, right? I mean, for example, what they need is like a ruler to measure stuff, or to take a picture of the things, or to see like a number or a graph or a bar or a specification. So the first steps are really rather simple, but still there's plenty of things you can do.
Yeah, but that's also the advantage when you develop your own hardware. You already can calibrate your camera so that you exactly know the intrinsic parameters. You basically, since you have two cameras and maybe an additional sensor, you can do a 3D reconstruction of at least points, individual points, and have something like an intrinsic model, like the whole lens canvas or something like that. So I don't know, you could already start something with that. Really nicely.
Sure. I mean, there are a lot of open source libraries out there, right, which can do this point cloud to meshing.
Yeah, but for example, if as I said, with the calibration of the hardware, you already have the intrinsic parameters. What you need basically is to put just some pattern on the table, for example, and you know exactly the extrinsic parameters.
The funny thing is that this pattern is already there.
Yeah.
It's, yeah.
and you also know the distances and everything, so you know exactly where you are, and you can then project everything right onto it. So yeah.
Yeah. That would be like the next step. The thing is, like, the good thing is the hardware itself is useful, and the content can be rolled out like gradually overnight. People can choose it depending on their needs. As we know, kind of, since we're from the field, like we're all scientists, we know. I mean, science is quite nice because all the email addresses are actually out there. You can just look them up, and you can also look up what they're doing and then guess what they need based on that, and then tailor the stuff to their needs. So that's also pretty practical. And yeah.
I think there's a nice library for that, the point cloud library. It's, that manages all these constructor points and everything. So you might want to look into it.
Okay. Thank you. So yeah, I mean, we're gonna look for developers in the later stages of our procedure or our journey. So that's why I'm here. So to keep it in mind, in case you know someone who knows someone who knows someone, you know. Yeah.
Okay.
Thanks.
I think we make a 5 minutes restroom break or fill up break or beer break or whatever, and then continue with my awesome talk. Thank you. Okay, so I think we can continue with the next talk. You can all mingle around and talk afterwards as long as you want. No problem. So, I will give you a short lightning talk introduction to CoreML. That's a nice new API which Apple will release with iOS 11. That's going to be in September, and then it will be pretty easy to do convolutional neural networks and other neural networks and machine learning stuff on native on iOS. So has anybody of you ever programmed on iOS, Objective-C? Is anyone interested in doing this? Yeah, some of you maybe, okay. So it's going to be a short intro, and then I'm going to do just a live coding to see how easy it really is. So for the intro part, so CoreML, it's a new API. It sits on top of BNNS, that's the low-level APIs for doing neural network stuff. That's C APIs, they existed now for a year, and now Apple announced a simpler new API, which is really nice and handy to do neural network stuff, and you really don't have to have any idea about neural networks and machine learning, and you can do everything. And it's really optimized to do on-device performance, low energy usage, low memory footprint. And it also, when you convert your neural networks from, let's say, Caffe or somewhere else, they do optimizations that it's run faster on the device, and they automatically decide if it's better to run them on the CPU and the GPU and whatever stuff. Really, all the magic is handled for you. But on the device, you can only do the forward pass. So you can only execute the neural network, in order to do the predictions. You have to do the training on Caffe, TensorFlow, and whatever, but it's also a nice tool that comes with it. It's a Python tool where you can convert any network to the Objective-C CoreML network. So that's how it's how it is. So you have your app, and on the bottom you have your Accelerate and BNNS, that's the CPU version for the neural networks. And then you can also do the metal shade performance shaders where you have the GPU neural networks. And you can also directly use these APIs, but they are pretty low level, and you have to design your whole network there. It's complicated. I gave a talk a few months back about this topic. And now on top of it, it's CoreML. That makes it all pretty easier. And on top of that, you can use even simpler APIs. If you do vision stuff, face detections, that kind of stuff, you can have even simpler APIs, so for natural language processing or for gameplay kit for AIs for games and such stuff. And you can use all those APIs. And they are all pretty easy, as I said. And key features, you can use neural networks, and the most popular layers, convolutional pooling, fully connected, where you can build most of the stuff. You can also use tree assembles, support vector machines, and also use generalized linear models. And for the converting tool, that's just a very simple Python tool where you can convert different models to CoreML models, and you can convert neural networks, tree assembles, and all these models with different supported tools. And Caffe and Keras are popular tools with neural networks. Keras is also used inside of TensorFlow. And Scikit is also a very popular Python tool for machine learning. Yeah, and you can, but it's beta, and I think there will come even more supported things in the future. And if your tool is not supported where you want to do your training, you can also easily write your own converter with this Python tool. It's just except from 2 lines of code, it's then maybe 10 lines of code. So, and that's it for the presentation part, and now I'm trying to do a live coding demo. Let's see how this works. Live demo time. So, we are now developing an iOS application where we use the camera and the camera frames and use the Inception version 3 model. I don't know if someone knows that. I think it's from Google, where you can classify 1,000 different objects, basically, and it's pretty good, and it's a huge model with a lot of nodes and things and stuff. And so, yeah, you can see the DXD, it classifies 1,000 different things. It can classify a volcano, a ball player, a corn, mushroom, yeah, a lot of stuff, basically. And I downloaded from GitHub, I don't know if you can see it, let's change this. Presentation. Yeah, that's better. So that's a Python script which creates you the Inception version 3 model, and it downloads all the weights and biases and everything, and then creates your whole model. And what I'm doing, I'm creating the model, and I'm using the labels from the DXD, where the 1,000 labels are classified, where you have the outputs from 0 to 1,000 mapped to the labels. And then I'm using this CoreML tool converter, and I'm loading it. It's a Keras model which I'm loading, and I'm converting it to a CoreML model. That's this line of code, basically. I just tell them how I want the input names to be named. Image, you can put everything you want here. I'm just telling him that the input is an image. That makes it easier, because then Apple creates a method which you can, when you do the prediction, you can simply use an image. Otherwise, you have to use an array and make the image to an array by yourself. But it's also handy if you tell them the input is an image, and then you tell him the output, the class labels is the labels, that he also knows that 0 is mapped to a dog and 1 is mapped to things, and that makes it also easier that you don't have to do this by yourself. And then I store this model just as ML model anywhere. I'm now running this script, and now we wait for probably an hour or so. No, it's faster than that. In the meantime, I start my Xcode project. We are creating a new project. We're creating a single view application, so we only need to have the camera stream, and we show the camera stream, and then we have a label where we put the predictions from the neural network on it. So we make a single view application. We call it Anyline CoreML sample. Yeah, put it on desktop. Okay, let's see how far it is. So we have 210 nodes already converted. And then for showing the video, we need a view. That's basically the system what shows you something on an Apple. So we create a view. We create a AL video view, let's call it. We don't need this code. Then we need a constructor for this view. That's we use the init with frame. That's the default constructor where we give the frame is the boundaries of the view, the width and height and the XY values. And then we create a init camera method where we initialize the camera stuff. void int camera. In this, we have to first set up a session. iOS handles all the stuff in sessions where they capture sessions. You can capture audio, video, and other stuff sessions. You can capture all the sensor data, whatever you want. You can use, therefore, an init session. So you initialize a capture session, and we set the present to 1080p. Now it doesn't know the session. Self is the dis for, in other languages, mostly called dis or something like that. So we define the capture session. I'm really fast at typing right now. Yeah, we have the session object. That's the property syntax on iOS. That's just a handy method which creates you a getter and a setter method and handles the ownership with strong. I give a strong ownership, which is something like when I have a pointer that I take ownership of the time. You can have weak or strong pointers where you retain the retain count, that it doesn't get released if another view also holds it and stuff. Yeah, it's not so important. Yeah, but it does not know the AV capture session, so I have to import the AV foundation stuff. That's where all the low-level camera and all the other sensor stuff APIs lays. So we have the session. On top of this session, we have to init the input. We have a video input, and we take a capture device input from a camera device, and we add this to our sessions. It's just a code which you have to use. And we also init the output. So we want to have a video output, and I'll make it a little bit larger. And we use these two lines. They're creating us this is creating us a queue, which is not on the main thread, and where we can get the sample buffer. That's the frames which come from the camera. They're coming in 60 seconds, 60 frames per second, and whatever. And with this method, you set that you want to get the frames on self. So I get it in this class. And I want to get it on the queue which I created. That's a queue which runs offside of the main thread. And this method just says that I'm discarding frames that will be late, or when I'm doing stuff on this, when I'm doing more stuff on this video queue, then the frames in between, I throw them away. And just when I'm done with the video queue stuff, then I'm getting the next frame. And then I'm initting the next thing, the layer. We also want to show what's happening on the camera on our view. That's what this code is all about. So I'm creating a preview layer, which is called an apple, and I'm setting it to bounce to my layer from the view. And I'm setting video gravity. I want to have aspect fill, and I'm adding the view as a sublayer to my existing video view layer. And last but not least, I have to start my session. What I'm doing here is that I say that the video orientation should be portrait. We only do portrait scanning right now. And afterwards we start our session, and then everything comes to life. So what I still have to do is implement this delegate method where I get the frames. So that's that method. Yeah, really fast. What it's doing, we get this sample buffer. This sample buffer is just a pointer on the video frame directly on the memory on the camera of the things. That it's really fast. That it can really provide you with 60 frames per second. And what I'm doing, I'm taking this buffer, converting it to a CV image buffer ref. And then on these lines of code, I'm transforming the image to be 299 by 299. That's what our inception model uses. It's just the scale conversion here. And this is just the conversion then to the pixel buffers ref object which my CoreML model needs. That's just creating this resize buffer, and I'm writing the CG context and I'm rendering to the CG buffer ref. And this method is for the future, where what the video view tells my view controller, which handles all the views for this app, what to do. And this one sends this buffer to my view controller. And I have to implement now this delegate shortly. That's just a design pattern like listeners on Android, something like this. So that's my delegate method, or my listener method. It's just how this pattern is used. So now we have our delegate. Why isn't it working? Oh. So now he knows the delegate. Or maybe not. Never do a live demo. I don't know. It should work. Expected identifier. Yeah, it works. It's just Xcode 9 beta. It's a little bit slower because I have the beta features CoreML, so I have to also use the beta Xcode version. Yeah, and that's it from the video view. I've set up the video view and I get the calls back. And then for the view controller, which handles all my views, I still have to tell them that we use the video view property. So we have the video view. I create the video view. I create the label, which is for the predictions, and I tell create an object for the inception version V3 model. It doesn't know now these types because I have to import the headers. So I have imported the video view and inception. It doesn't know this one because now the conversion should be done. Yeah, everything is done. We have the 330 nodes converted. And then I can use this model, which I created, and drop it here somewhere. And then Apple should create me this interface and my model. Now I have this code, now it knows it. Just initializing here the views. So I'm calling this constructor for my video view. I'm setting the delegate that I receive the frame stuff, adding it as a subview, creating my label, also creating my inception model, constructing it, and then I have to implement the delegate. So where I receive the pixel buffers, and that the only thing which I have to do is call the prediction from image and add the make pixel buffer, and if there are error, I can get an error back here. And then because I have to do the drawings on and UI changes on the main thread, I'm dispatching to the main thread from my Anyline video queue, and then I'm setting the prediction label text to the classification label which he classified. And that's already from the txt file 0 to 1000 prediction classifications. And that's basically it. It's a little bit more code because I have to set up the whole video stuff but it's still pretty simple. And I'm running this now on my iPhone. Yeah. One second. The building and deploying wireless takes some time. Oh. I have to switch to the other Wi-Fi because I'm here on the guest Wi-Fi because of the beam. Where's the Manisha? Welcome. Everybody meet up. So. Now it should work anytime. I could also get my cable, then it would be easier. Does anyone have an iPhone cable?
Why do you have an app for an egg timer?
For what?
An egg timer.
I don't know, because I have everything, basically. The wireless deployment is also a beta feature of the new Xcode, so
Works perfectly.
yeah. Before it worked. So now it's working. Yeah. So we have the video view and it's doing predictions, live predictions. So it's predicting a notebook computer. It's predicting, what does it predict here? A build bottle. Yeah, I don't know. Maybe we have something else to predict.
Oh, it is an antidepressant.
Let's see what we can predict. You can also predict a regular band. Yeah.
The thing is that the inception model is trained on images where the main object is in the middle of the image, so that's why usually.
But it's pretty fast. It works in real time, probably on iOS, and it's not. It has a lot of nodes. This model, and it's not so small. And on the performance of the model, I can't do anything. That's Google faults, basically. Yeah. But that's basically it, and that's my talk for today, the introduction to CoreML. Thank you. Any questions?
Did you try other networks, other pre-trained ones? I mean, because there is ResNet.
Yeah, no, I just did my first things in CoreML 2 hours ago, 3 hours ago, maybe.
Okay.
Yeah, first. So it's really on short notice, but it works very nice and it's very fast and easy. most of the stuff which I had to do was the setup of the camera. So really for the prediction stuff, it was converting 2 lines of code, and then the prediction was also only 2 lines of code or 1 line of code. It's very easy, yeah. And you can really convert. Apple already provided a lot of samples which they converted, but you convert any CAFE, Keras model which is out there, and that's really strong, really good. And do live on-device predictions, yeah. But I didn't try anything else, yeah. Any other questions?
Maybe a more general one. I'm not an expert in iOS development, or I have no experience with that, but what's your opinion on the impact of CoreML? Is that a toy, or is it something huge that everybody will use, or somewhere in the middle?
I don't know yet, yeah. But I think it can be huge because it makes really machine learning easy for everybody out there, yeah. I think you don't have to have any machine learning knowledge and can use the most complicated networks and run them directly on your hardware. And that's also what Apple is internally doing with all their computer vision stuff and the photo stuff and everything. Everything is run directly on the smartphone.
But you could do that before, but it was way harder to, or was it basically impossible?
No, it was possible, but it was way harder. I did a talk about this 3 or 4 months ago here in the Meetup. And there you had to set up all your nodes manually. You had to create your fully connected layer. You had to create your convolution layer, your pooling layers, and you have to put them together and everything, yeah. And now there are simple conversion tools, and just load them and everything is run, and you don't have to even think about running it on GPU or CPU, which is more efficient. Apple will take care of all the stuff. It's powerful, but if you are a professional in this topic, you maybe want to have more control over it. So that's maybe, but I think that will come in the future. Apple normally builds up on, tries to build in the first step the most simple version of they can imagine, and then add more complicated stuff to it in the future.
I think the good part about it is that actually you have an API or like an interface directly from Apple where you actually do all your training in the tool you want. TensorFlow, Keras, CAFE, whatever you want. You have your model with your weights, and you have one access point. You basically do the transformation of the model into this format that the Apple API uses, and you can use it directly, supported by them. So that's the thing. Because before you train it in one framework, you try to compile the whole thing as a library for iOS, put it on iOS, and then
So
it takes a lot of time.
You can separate the work where you have one machine learning guy who does the model, and then you just import it and have the iOS guy implement that.
Yeah, you don't have to port TensorFlow to iOS or CAFE to iOS, which there are ports and it works, but also Apple has a much more performance-oriented API, and it runs really fast on their chips. TensorFlow could never run as fast as this API on an Apple device because they take really use of the Apple hardware, because Apple also builds their own chips, so they can control the whole pipeline, and that's really strong. Google tries also the same thing. They also provides now in the future in the Snapdragon processors special parts of it for TensorFlow, that it also runs faster.
Yeah,
but
it uses the digital signal processor for running all the individual parts of the network, like from TensorFlow, what they have. And it's, I think, 10 times faster than just using the libraries and specialized hardware from which they have a collaboration, for example, Qualcomm to do a Snapdragon. It's the same thing. Apple, since they have their own hardware and exactly the interface and everything, they can optimize really well for it. And when you already have the model, you just transform it.
And they take care of the optimization for their hardware. So by transforming the model, it will get optimized for their hardware.
So if you have, for example, 5 applications that use a neural network, you don't have to have each a library with neural network implementation in each of those applications. They might just connect to this interface, and the applications themselves are less closely together.
Yeah.
That's quite a huge advantage of it. And it's also, for example, for scientists, if they basically try new things, new models and everything, they just don't have to do a lot of the low-level stuff, just deploy it on the iOS.
But back to the original question, if this will have a huge impact, I think there's another SDK which will have even more impact. That will be ARKit, which provides very easily augmented reality to all iOS devices. I think that will have an even more impact than the CoreML, because then you can really do as simple as CoreML. You can do augmented reality without having any AR knowledge or computer vision knowledge, and that's also very nice. Yeah. But I will present this probably at the next meetup. ARKit. Any other questions? No? Okay, then thank you for coming at this hot, nice day, summer day, and feel free to mingle around and grab another beer and talk to me or everybody, yeah, and have fun. Thank you.